Now let's look at the technicalities. You know how the minimax algorithm works, but how do you use it in your code? We are going to look at the algorithm as such, that is, the steps you need to follow to implement this algorithm in your code. So first of all, let's look at some common terminologies used in this algorithm. So as I explained before, the minimax algorithm is used for two-player games and nothing else. And one of the players is called the max and the other is called min. I explained why that's the case in the examples we looked at above, and the max player always moves first in every iteration of the minimax algorithm. I already told about this as well. Also, at the end of the game, points are awarded to the winning player and penalties are given to the loser. So in our case, the winner will get a +10 and the loser will get a -10, and if it's a draw, no one gets anything, which is 0. And as you know, these values can be changed. It's what we set up, okay? So before we depict this in the form of an algorithm, let me explain certain terms that we'll use in our algorithm, okay? So the first one is SO, that is initial state. This is the initial state of the game or the board. In a tic-tac-toe game, this indicates a completely empty board where all the 9 boxes are empty. And then player of S. So the S in here refers to the current state, and player of S means the player who has the right to make a move in that particular state. Okay? So next is action of S. This refers to the set of legal moves that the current player can make in the current state. In a tic-tac-toe game, this will refer to the number of empty boxes on which the player can draw and which particular boxes they are and what are their numbers and so on and so forth. Okay? The next is result of S, A. So in a state S, player of S made a certain move which was described in action of S that I already told you about, right? So because of that, we'll have a new state on the board right now. And this particular state or this particular result is depicted by result of S, A. Finally, terminal of S. So every time a player makes a move, the terminal test is run to check whether the game is over. So if it is, that is if someone has won, or if it's a draw, then the test will return true and the result of the game will be evaluated. If it's not, then the test will return false and the game will move on to the next state. Then finally, there is utility of S, P. This is the utility function, also called the objective function or the payoff function. This defines the utility or the final result of the game that ended in the terminal state S, which was last played by the player P. As I told before, this utility function can come in any form. Usually, if the player wins, they'll be awarded a positive number as utility, and if they lose, they'll be awarded a negative number. Why so? Well, I already call these games as zero-sum games because, as the name implies, there can't be two winners in these games. When one player wins, the other loses, right? So if the final state of the games are +1 for win and -1 for lose and 0 for draw, then when you add all of these up, +1 plus -1 plus 0 is actually 0. That's why it's called zero sum, because there can't be two winners and the sum of all of these utility values is actually 0. Do you remember the game tree I showed you before? This particular game tree? So this game tree is created by using the initial state, the set of actions that the players can make, which is represented by all of these leaf nodes, that is all of these children, and then the final state or the terminal state with their utilities. In here, these are the terminal state and they have utilities written below them. So as I explained before, we have a game tree which depicts the entire state. This is the game tree that's depicting the entire state. The max player in here, which is AI in our case, this player is going to play first. So this player goes first, which is usually the AI. But this can change as well. The max player can also become the human, so that's up to us. But since the minimax algorithm is usually used by the AI to make optimal moves or to find out optimal moves, in whichever state it uses it, it'll be considered its initial state. So the AI will automatically become the max player because the minimax algorithm is used by the AI. Okay? Because a human player does not need a minimax algorithm. We have our brains, right? So for example, if the AI only starts from the second move, it'll create a game tree based on the state of the game after the human player plays in its first move. So it'll choose the optimal action at that point. That is, it'll choose the optimal action for its second move. That is for the second move of the game. Then the human player plays the third move, and then for the fourth move, the AI will once again create a game tree based on the state of the board after the third move played by the human player. Now it'll find the optimal move for the fourth move with that tree, and then so on and so forth. So every time as the AI's move, it'll create a tree just like this. It'll create a new tree just like this, where the first particular root node is the state of the game at present. Okay? So no matter where the AI starts in the actual game, when it stimulates the game tree for the minimax algorithm, it'll always be on top of the tree in the max position. Right. So in the next lesson, let's look at the pseudocode of our minimax algorithms. I'll see you there. Thank you.